Okay, perfect. So thank you everyone for coming. This is going to be, I hope, a nice but also a short talk by Raul about some work that he has been doing recently. And especially the idea is not just for you to see the work, but also to see how you can use what he will present, that is database actually, in your own research. So hopefully you will find this useful for the future. So, well, you know him, he's a PhD student here, so I don't think that any additional introduction is necessary. Perfect. So the floor is yours.
Thank you very much, Massimiliano. I don't know. I think.
Yeah.
Okay. So actually, you said it's going to be short. I think it's going to be the longest presentation I've ever given, but still on the time we talked, so no worries. So as you can see from the title, what I'm going to do is introduce a large-scale data set of networks that have the following properties. First of all, they are temporal, they're spatially embedded, and then we are going to discuss also how they can be multi-layer. So just to put a little bit epic. Anyway, just no. Okay, I know what happens. Is this thing? What is not working? Okay. No. No, it was the presentation anyway. So just to give a little bit more of context of the data set, I will speak a little bit, just very short, about my PhD. So the title of it is Aircraft Interaction Modeling through Complex Networks, and more in practical terms, basically the steps of my PhD is building an aviation-related data set, analyze it, this data set as a complex network. So we need a data set that can be translated to a complex network, and then with that analysis, using all the framework of complex networks, try to get information about air traffic dynamics. Now, the current point of the PhD, we have all the data set built. That is what we are going to show here. But we are on the second part then. But in this presentation, what I'm going to focus is specifically on presenting the data set that we built, and that it's completely open for you to access. So now the first question that we have to make is, what is this dataset? What does the dataset contains? And the whole idea is that for each day, we have recorded all the events in which pairs of aircraft fall below a threshold distance, analyzing all the trajectories over Europe. Now, what does it mean for two aircraft to fall below a given distance threshold? So imagine that we have an aircraft and we build a cylinder around it. The specific values of the thresholds that we use are not relevant for this presentation. We can talk about it if you want afterwards, but in principle this would be more if the talk was oriented towards people in aviation. So just think of a cylinder that makes two thresholds, an horizontal one and then a vertical one. Whenever another aircraft enters into this cylinder, then we are going to record this event, these two aircraft falling below the threshold distance. And this is basically how the dataset is going to be built, constructed. Now, the next question to answer is, okay, how can we build an actual network from this dataset? And at least the approach that we took is extremely straightforward. Its node is going to be a flight, and two flights are going to be connected via an edge whenever this distance threshold is violated, whenever both of them fall below this distance threshold that we commented. Then we are going to add information on the moment in which their horizontal distance reaches the minimum in order to be able to generate this, to give more information and generate these different types of networks that we commented. Now, this is the theory. Let's put it a little bit to exemplify it with an example, so you can get like in real time how the data set is constructed, and maybe it's a little bit more visual. And here on the right side of you, no, on the left side of you, you have an airspace. So this is like, of course, something made with Python, but the data is the data from the actual trajectories. Here in blue is highlighted a sector, simply like a chunk of airspace that is basically like controlled by a group of air traffic controllers. You will see why it's relevant in a moment, but for now you can forget it. Then the triangles are going to represent the aircraft, and in this case, we are going to assume that all of them are going to fly at the same altitude. So in terms of vertical, they are always violating this distance. So the only thing we have to worry for this case is whether they violate the horizontal one or not for them to be included or not. And in this case, the horizontal one is given by this circle here. So whenever two circles overlap, it means that we have an event of this kind. Then this thing here on the right represents the actual data set, the thing that you can download, the CSV file that you can download, and we will see how the information is added there. And finally, to complete like the whole translation, what we see on the airspace to the network, we are going to build in real time the network, the translation of the dataset into the network. For now, as we have two flights that they have, let's assume that this is the beginning of the day, so they have not fallen below the distance threshold, we simply add them as two isolated nodes in our network. So we start to see the evolution. One enters in the north, and we see that they are already overlapping, so this is going to be an event, but we wait until the distance, the horizontal distance, is minimum for us to add it to the dataset, and we can see it on this row. And of course, this would translate into the network because first of all, we have added a new node corresponding to the aircraft that entered, and now this one is connected, which represents this event here, this entry on our dataset. If we continue a little bit more, we see this one is going to enter now, and these two are again having this interaction, this falling below the threshold distance, and hence we wait until they have reached the minimum horizontal separation, and we add them again to our network, and this will be the whole idea. We process the trajectories, we build this dataset, then we convert it to the network, but this is what you are going to find in the dataset available for download. So this is the whole idea. This is a little bit trivial in the sense that this was an example, but the actual networks that you get when you process an entire day of data look something more like this, which at least they definitely don't look like networks of 4 nodes and 2 edges as we were seeing before, and at least for me they look quite complicated. And in this case, this network corresponds to the 1st of September 2018 for all the flights over this region only, that basically is this region and not any other, because this is controlled by one air traffic control center. So now that we know how the networks are built and like the overall idea of the dataset, let me first explain very quick some nuances of the fields that you are going to find in the dataset. So the first two rows are going to be the flight identifiers. So these are not going to correspond to, for example, identifiers used on the original trajectory file, or for example, if you have one flight from Madrid to Palma at 5 in the afternoon, the next day, the identifier of that same flight is not going to be the same number. They are anonymized and randomized every day. Then, in terms of the time, this is the timestamp in which the event takes place. This time is offsetted and is the time elapsed since the first event of that day. So in every file, there's going to be one event with time 0, which is the first one in that day, and then we start counting in seconds from that moment to set a time for our event. The good thing, in case you want to construct a temporal network, is that the time distances between events are respected. So with that information, we still have it. Now, in terms of this distance, as we mentioned, is the minimum horizontal distance reached in nautical miles. The altitude, basically it's given in flight levels. That is another unit of how to measure altitude. In case you are interested, it's equivalent to one flight level to 100 feet, in case you are more familiar with it, but it works the same way. The bigger the number, the higher the plane flies. And it's rounded to the closest multiple of 10 flight levels, because usually airplanes tend to fly on these multiples, on these flight levels that are multiple of 10. And finally, the feed ID, that you can consider simply as the sector ID, is an identifier for the sector in which the aircraft is flying. So, for example, in the example before, this 65 corresponded to Macedonia, that was the sector that I was showing, but in this case is anonymized with a number, and this number is respected between days. So number 65 is going to be Macedonia in all the days of the dataset for you to being able to compare. So this is a little bit very quick explanation of the fields. Let's now go to what I find the relevant topological characteristics of these networks, or what it makes them a little bit, let's say, interesting to treat from a pure complex networks point of view. The first one is that these can be weighted networks, because we have here the minimum horizontal distance that they reach, and this can be used as a proxy to basically weight the edges of the network. Then they are temporal, because as we have mentioned, we know when the events take place, we add it, and despite it being an offsetted time, it respects the distance between events, so we have a chronological order in our dataset. Then they are actually spatially embedded, because we know the altitude in which it takes place, and also longitude and latitude, it's encapsulated in the sector, because the sector is defined as a range of latitude and a range of longitude. And also, there can be different multi-layer representations that we can think about. I'm giving here you one of them, which is using the sector. We can create different networks depending on the sectors, and these networks are going to be connected. Why? Because the flights usually tend to fly normally through different sectors. So we are going to find one same flight, of course, at different times of the day in different sectors. So this way, we can create different layers, each one for a sector, and these layers might be connected through the different flights. Now, why are these networks, why are these datasets relevant for in terms of what they represent in the real world? They are quite complex, and they are quite complex in different layers, because they are the result, in the end, the traffic that we find in the skies are the result of a lot of, I've said 3 different layers. All of them themselves individually are quite complex, but they also are interdependent one of the other. So the first one I've called social, economical, political, because they are interconnected. Also these 3, as they are quite tight, as you already know. And if what does it mean social? So social, for example, means that the routes and the frequencies in which aircraft fly depends completely on the demand. That is something that comes from the social area. For example, it's social, the reason why we have here in summer much more flights to Palma than, for example, in winter. Economical can be, for example, that is a recent news that basically said that Ryanair abandons Valladolid airport, which is basically a pure economical reason. The national service provider of Spain said, I'm going to raise the fees, and Ryanair said, okay, bye, no longer interested in flying to your airport. And also political. We already know the situation Russia, Ukraine, and basically the whole closure of the Russian airspace had massive impacts in the trajectories that aircraft fly. Now, there is yet another layer, which is all the engineering technology layer, which is actually how, from a theoretical point of view, the airspace is controlled, the airspace is organized. So first of all, we have the engineering side, all the documents. For example, this one basically tells you how you are supposed to control from a theoretic point of view. There are also a lot of different documents on how to deal with the capacity of the airspace. And also from the technology side, depending on the technology that we have, we can fly on one way, like we can generate one way of the trajectories, or we can do it on a different way. For example, the way we fly in mainland is completely different than the one they use when flying between Europe and the United States. And also, we rely a lot on this technology. If for some reason one radar falls, the airspace usually, well, not usually, it gets closed, and this generates changes in the trajectory. So there is also this layer that then is seen in the results of the data. And finally, all the previous one that we have talked is from a theoretical point of view. Of course, the controllers follow what they are told to do and what they get educated on doing, but in the end, when the real situation comes, it's their decision, and in a micro scale, there is a lot of human factor and psychology on taking the decisions when two aircraft get too close or on how to organize the traffic. And of course, not every person controls the same way, and not every controller has the same kind of mood every single day. So in the end, what I want to say with all this is that they are networks that contain very complex information, maybe too complex to even untangle, but definitely they are not a trivial like, okay, it's every day it's going to be the same. No. So now that I have motivated a little bit these networks, let's see the actual data set size. The first thing is that we have data for 854 days that span 7 years between 2015 and 2021. And we have analyzed all the available days. It's not the 365 days of the year. We only have 4 months per year. This is because of the restriction of Eurocontrol. But the good thing is that we have March, June, September, and December. So basically the two different seasonalities that we see in the year, like low season, high season, we are able to see in the data that we have. We also have for executed and planned trajectories. So planned trajectories are the ones that before the operations start, the aircraft are meant to take, and the executed ones are the ones that they actually took, the ones after the operation, that day of flying took place. So in total, we have 1,708 files, making for almost 24 gigabytes of compressed data in Zenodo. And this was the result of comparing close to 9 times 10 to the 12 pairs of flights. So thanks to Nureduna in this case. And now, if we take one data set and we ask ourselves, okay, what does one data set from the collection has? It has these events recorded for 24 hours, so the entire day, and for the trajectories flying over all this area of Europe. I agree, it's not the entire Europe, but it's quite close to it. And as you have seen it, we classify on these events depending on the sector in which they take place. So overall, on average, we get networks with 22,000 nodes and 49,000 edges. So in terms of validation, the biggest problem to validate this data is the fact that no other data set of this kind exists, done with other type of trajectories or with other type of pre-processing. It does not. So this basically limits a little bit what we can do, but we try to take an approach like trying to validate the data itself to make it, if it made sense. We have testing on the code independently. I developed the code, Massimiliano developed the testing. We studied the discarded data, so the data that we did not use, the trajectories that we did not use, made sense for them to not be used. And also we analyzed the correlation between the number of losses of separation, these are safety events, declared safety, like unsafe situations recorded by Eurocontrol, and the number of interactions, and we saw a strong correlation when comparing both of them. So when the number of losses of separation increased, the number of these events that we recorded also increased. But if you are interested in more information about this validation and in general, more information of anything I've said before, you can go to this article here that basically contains all this explanation, but much more in detail. Now, to this data set, that was the main one, the one I wanted to present here, there are also two additional sources of data. One that you will be able to download, that is what I've called metadata files. These metadata files, basically what they contain is information about the global state of the airspace that day, divided by the sectors. We have the -1 in the FIR ID, in the sector ID, is the entire European airspace, and then we have the same numbers as before. So, for example, here, the sector 65 and the other sectors of the airspace. It contains the total number of flights, that this thing, for example, is relevant if you want to calculate, I don't know, the ratio of isolated nodes the networks have. You will need this data here. Also, the total distance flown on that sector, the total time flown on that sector, and then two measures of the entropies of the trajectories. I'm very sure that you are already familiar with entropy, with Shannon entropy. That's the one that we have, but basically it's simply an estimation of how homogeneously distributed the trajectories are on this sector. And if you are interested in seeing specifically how we used this measure for analyzing these networks, you can go to this work here. And then there is yet another one, which is extended information. This one is not included. I will go in a second why, but it contains the exact longitude and latitude of the event. So before we had the sectors for altitude and longitude. Now with this, we can pinprick exactly where the event took place, more information about the flight. So this time you can know, okay, this Madrid Palma at 5 p.m. in this file is this one, and in this other one is this one. The actual time, like the UTC time, not offset it, and also the names of the sector. So now it's not 65. With this data set, it will be Macedonia, North Macedonia. Now, why it's not included? Is because of this data provider of Eurocontrol. That we had to anonymize a little bit the dataset. But the way to access it is extremely simple. You just have to show proof of registration in this data archive, and it's completely free. I did it like 4 months ago. You simply have to say like, okay, I'm from this university, send them the message, you get approved in a matter of 1-2 days. So if you think like, okay, what I showed you before is not enough and you want some of this information, get in contact because it's trivial having this data, and we have it already created, so we can share it with you. Okay, so now I think like the data itself is introduced, and now it begins a little bit like the second part of the talk. That is basically how we wanted to orient this is how we could see that these networks can be used to tackle or to approach ongoing challenges and ongoing topics on the complex network world, on the complex network framework. We are going to give you some ideas that we have, so we are no expert in, well, at least me, I'm no expert in any of the topics specifically that I'm going to talk, but we, like when, for example, when writing the article, we thought a little bit on how they could be used, and also trying to justify why these networks are interesting specifically to use in these applications. But I have to make a warning, the applications are going to be non-aeronautical. I think now you are extremely happy. Maybe Pau is not very happy, but the rest of you, I'm very sure you are extremely happy. I'm extremely sad because they are non-aeronautical. But I hope this way no one leaves. So now if someone leaves because they are non-aeronautical, I'm going to be extremely sad, even sadder. But if someone wants the aeronautical applications, you can find a better suited presentation here. You don't have to scan it now. I can share afterwards with you if you want, that I gave at a workshop last year. So the first one, it's extremely straightforward, which would be testing topological metrics. We have a metric that I invented myself and I want to test it. So these guys have a new closeness centrality measure. Of course, you can test them in this network, but I guess on any network you can do that. The good thing of these networks is that then if you start to see new new metrics for weighted networks, for temporal networks, these networks, they can also be a test bed for these networks, because these networks that we are presented are weighted, these networks that we are presented are temporal. So maybe these are not characteristics that every network has. And I specifically I start on metrics for similarity, distance, because we already worked a little bit on trying to see if we were able to find differences in the topology of this network based on characteristics outside the networks, like more macro scale variables of the airspace. So for example, here saw that there is a clear difference. Here we are plotting the total distance flown as a function of 2 metrics here, but this extends to a total of 6. And we see that there is a clear relationship on the structure of the networks with the total distance flown, and also a very interesting one between the day of the week. We see that the weekdays behave on a certain way, but then Saturdays and also Sundays to a lower extent, they behave kind of different. So the good thing is that with this result, it's already kind of a base to see, okay, if this metric is telling me that, I don't know, one of Tuesday and Wednesday are extremely dissimilar, and then one Saturday and Thursday are extremely similar, here it's the opposite. So it's a little bit of result that maybe you can leverage if you have this type of metrics, you want to test this type of metrics. Then we go to another topic that is quite ongoing in the complex network world, to call it somehow, which is network classification. The overall idea is have networks that come from a similar background, have something in common between them that they do not share with networks of a different background. So for example, in this article here, what they did was they took social networks, citation networks, that these have this thing in common, this topic in common, and by analyzing different networks, what they saw or what they tried to see was, okay, is this metric a specific values within the social networks but completely different to the other ones? And basically, the interesting thing of this article was also that for the different ones, the transportation domain was the one with the lowest number of networks. That is something that for me doesn't surprise me after 2 years of working in this world and seeing how much data about transportation we have. So with our network, you can go to 6. It's still not the order of magnitude of the other ones, but hey, +1, I don't know. So yes, this is something also that you can add it to your transportation portfolio to analyze it. Then the third application that we thought would be network dismantling algorithms. In short, in case you're not familiar with it, we have a network and we have to find the best way to basically destroy it. So here, for example, we have different methods. This is not mine, this is from this article here. Different methods, and here what they say is how much the giant cluster is destroyed as a function of how many nodes we have attacked. Basically, this to test the robustness of the network. Now, this is also interesting for the data set that we propose, because in our case, removing the edges have actual operational meaning, and depending on how you do it, it might have a different operational meaning. So, for example, if we start taking edges, individual edges, then what we are doing somehow is rerouting. If we take just one edge, somehow it's rerouting. It's saying the aircraft, okay, you have not flown this one, you have flown this other one. And by flying this one instead of this one, what you have done is to avoid one of these events. So this would be, for example, the meaning of removing one. Now, if we do it in more mass quantity, so for example, all from an aircraft and we delay them on time, then what we would be doing is to delay the aircraft. And if we completely remove them, what we would be doing was canceling the aircraft. So what I mean here is that they have an actual meaning depending on how we do it. And also the interesting thing of these networks is that while other networks, they try to be robust, these networks, it's the other way. If we are able to destroy them very soon, it's better. We don't want them to be robust because in general, despite these events not being necessarily safety related, the more we can fly separated, the better. The less work we would have to give the air traffic controllers. This is something that we explored very superficially in this work here. Very trivial methodologies for different metrics. You can see here better in efficiency. This dash line, this the set score. So comparing with the random one. When we attacked randomly, like when we removed randomly, this other one, like the solid one, is when we did it basically like attacking the one with the highest number of connections at that moment. Again, nothing crazy results, but just in case you want to see some starting point, here it is one. Then another interesting topic, higher order interaction. So we have this, like I'm no expert neither on the other ones, but less in this one. So I took like this paper that seems quite canonical. And in the abstract, it says that networks are described usually pairwise interactions, but in some real-world system, the interactions that matter are the ones that take place between more than two elements. And actually, this basically what this is telling us is that this is actually like how we normally analyze a complex network. And for example, how I have been performing the analysis of the complex network. By pairs, which means that this interaction exists but has nothing, but we could eliminate this node here because this one is just between these two, and the same with the others. What high order analysis is proposing that if there is a triad that they are all interacting with all, then we cannot say these two are interacting and we forget about this one. We have to consider the three of them. And I have to say that for these networks, this theory makes complete sense because if we go to this example of a simulated airspace, at 640, we have this event here that we added to our network. 642, this other one that we added, and 644 that we added again. We have again this fully connected 3 nodes network. But now, at any moment, if we analyze and think that the same air traffic controllers are taking care of the entire airspace, we can say that when this second interaction occurred, the air traffic controller was only looking at these two. For sure, he was also paying attention to the three of them. So it makes sense in these situations in which there are these triads of interactions in a short time and space to consider that they actually are interacting, the three of them, that they are generating a situation in which they must pay attention to the three of them at all times, not by pairs exclusively. And in the dataset, this can be extremely easily found. So basically, we filter to find the triads. We, for example, say, okay, they have to be in the same sector, so the same people are controlling the three aircraft, and also a maximum temporal separation of, let's say, 4 minutes. So by applying this filter, we have here one triad that would be, again, an example of the type of structure that I said before. The lower the temporal separation that we put, the more sure we are that they basically have been relevant, the three of them at the same time, but the less likely we are going to find events. So another application, just this and another one, and we are done, would be community detection. And at first glance, you might think, I mean, the edges are created spatially. So we need special conditions for the edges to be created. Of course, the communities are going to be extremely trivial. We are going to have high density zones that are going to be extremely clustered, that they're going to represent a cluster, then low density one, and then another high density one of space. And that is going to be this way, like the communities are going to be extremely trivial. But the thing is that I wouldn't think so. Why? Because this would work if, for example, the flights in France only flew between France, the flights in Germany only between Germany. But there are a lot of flights that actually fly a long distance in Europe, and through this long distance, they might pass through different high and low density, and they are going to connect the different clusters that we might or might not found. And additionally, not every sector is controlled the same way. So depending on the sectors, some sectors might deal with the same density of traffic on one way or on the other. So I would not expect the communities of these networks to be extremely trivial. Again, in this same article as before, we again apply like the Louvain algorithm, but not with the focus of specifically testing community algorithms. This was more like exploratory and setting something like seeing what was going on in general terms. And we saw here that, for example, when we compared with the random network, modularity was quite high, but again, it's something that I think it's worth giving another go. And the final one is link prediction. That this is again another topic that is up to date in complex networks. That is, given a group of networks or a network up to a moment in time, am I able to predict the existence or the non-existence of a link either from in a different network or at a future timestamp? And so basically the idea would be this: if I have this network that it has been created up to 1030, then what I would like to know is if at 1035 this edge is going to exist, or I'm going to have the same network, to put a very simple example to give the idea. The thing is that with the data set also, this is interesting because we have a lot of different days that in the end they represent the same system. Of course, it's not going to be exactly the same for all the nuances that I mentioned before, but I think it's a quite nice database for it to learn on what has been happening on the past, and it's also quite large scale. And also from a practical point of view, this is extremely interesting because if these algorithms work, if we can know 5 minutes before the situation that we are going to have one of these events, for the air traffic controller definitely is interesting information. Maybe then it's not something safety related whatever, but definitely it's interesting having this predictability power on this network. So again, like just very quick ideas that came to my mind, but this is more just to try to inspire you or to say like, okay, this one I find interesting. I would do it completely different, as you mentioned, and for a completely different reason that you do. But that was precisely the point of trying to bring this up. So this would be all. If you want to access the dataset, it would be this link here or this QR code here. More information about the dataset, which means this presentation extended to 14 pages, is in this contribution here. And in case you are interested on, okay, how have we used this specific data set more aeronautically related to find information or to analyze the networks, you have these other works here. And well, I mean, this is more if someone then watches the recording, typical 3 a.m. YouTube algorithm recommendation, you can contact us here. But of course, you from MIFISC can come to my office anytime and I would be more than happy to talk with you about this. And that would be all on my side.
Okay, thank you very much.